In the last video, we started proving this property, property 9, which says that the determinant of a product is the product of the determinants. And the idea was to define a new function called determinant of A and define it as the determinant of the product of AB over B for any invertible B. And to show that this is actually the same determinant function will give us the result. Okay, because then we can multiply both sides by b. And so we're trying to basically show that this is a determinant function, and it's the determinant function. So to do that, we showed that it satisfies the first two defining properties, okay, of the determinant of the identity is 1, and interchanging two rows changes the sign of the determinant. In this video, we're going to show linearity. We're going to show that this definition satisfies the linearity defining property. Okay, and it's kind of messy, but if you follow along really carefully, I think you're going to get it. So to start with, there are two things to prove with linearity. One is a constant multiple, and another is addition. Okay, so here we're doing the addition. So our goal is this one here. This is our goal, is to prove that using the DET formula, okay, here to save space I'm just writing the regular. So it's to prove that if I were to take the determinant of this matrix, then I could take the determinants of these two matrices and add them. Okay, that's linearity. But I'm going to do this very carefully, and we really have to understand matrix multiplication. Okay. All right, so let me start with this, and let me just write it again here. So we have x plus a11, y plus a12, and z plus a13, and here we have a21, a22, a23, a31, a32, a33. Okay, and so according to the definition, this is equal to the determinant of the matrix x plus a11, y plus a12, z plus a13, etc. times b. So it's the determinant of that product divided by the determinant of b. That's just the definition that we've established, and we want to show how linearity plays out. Okay. Now, let me go back and show you what the C represents. Okay. So in the very beginning of the last video, we said that AB equals C, and so C is written this way. And we know that the row responsible for this first row of C comes from the first row of A. Okay? So if I change the first row of A in any way, that's only going to change the first row of C. Okay. Now how does it change it? Well, I'm changing the first row of A by just adding X, Y, and Z respectively to the three entries. Okay? And so the way that changes the product is we get, so let me just write this as 1 over the determinant of B. So the way that changes it is that I still get C11, but that is adjusted by some value due to the X that we have. Okay? And then the second position would have C12 plus some other number and C13 plus some other number. Okay? And these won't change. Okay? So that's what happens when you multiply or when you add that quantity to the first row of B. So that's how the product is adjusted. Now using Now this is just a regular old determinant, okay? So we can use the linearity we know to expand this, and we would get basically C11, C12, C13, C21, C22, C23, C31, C32, C33, plus X prime, Y prime, Z prime, C21, C22, C23, C31, C32, C33. And of course, both of these are multiplied by 1 over b. So I could just put this as over b, the determinant of b, and this is over the determinant of b. Okay, we know what this first thing is, right? The C matrix, this is basically the determinant of AB over B, right? Plus, now what is this? Well, that X prime, Y prime, and Z prime, who's responsible for that? Well, that comes from replacing the first row of A with X, Y, Z. This is A21, A22, A23, A31, A32, A33 times B. Okay? And there we are. This is basically the determinant of A plus the determinant of X, Y, Z, A21, A22, A23, A31, A32, A33. And this is very nice because now we've shown that the determinant of this was the determinant of, let's write it down, the matrix X plus A11, Y plus A12, Z plus A13. This determinant basically follows linearity. Okay, so you can break it up as the determinant of the ones without the x, y, z's, keeping the second and third row unchanged. That's right here. And the determinant with the x, y, z's, but without the other a's, and keeping the second rows unchanged. So this follows the linearity. Now the other property that we need to show for linearity is multiplying a row by a constant multiplies the determinant by a constant, and that's quite easy to do, much easier than this if you think about it a little bit, as to what happens in matrix multiplication if you multiply one of the rows of the matrix on the left by a constant. I'll let you think about that.